Hello BNG319 class, welcome back. Unfortunately we didn't get through all of our lecture on the final exam topics that were most important to all of you. So here's the rest of it, probably about 10-15 minutes here in a little YouTube video. So we stopped at exactly where I was about to talk about surface chemistry. So this is of course a recent topic. We discussed adsorption, which of course, as you know, adsorption is different from absorption. Adsorption is attachment to the surface by some interaction, whereas absorption is actually penetration into the bulk material. And you can see the surface here on this little diagram is represented by orange spheres, and the bulk material underneath is represented by green spheres. And typically what we see, what we can touch on surfaces like tabletops, laptops, skin, that sort of thing, are the surface, the orange sphered surface here, where we can't really get into the bulk material underneath unless we start, cutting things in half and whatnot. Then we can see the bulk, but then the bulk material becomes a surface, and it goes on and on and on like that. So let's just consider the surface and not worry so much about the bulk material right now. But what makes a surface special? Like, why should we do that? In other words, why does adsorption happen? Adsorption arises due to the fact that surfaces are special. Surface particles of the adsorbent, so if we imagine that this is an adsorbent, the adsorbent is going to occur on the surface. They're not the same as the particles that are inside the bulk. In the bulk, these green spheres are surrounded by other spheres on all sides. And this is, this is what it is. It's a fact. They're completely surrounded. So their interactions are all satisfied. What kind of interactions? It doesn't matter what kind of interactions. It could be hydrophobic interactions. It could be ionic bonding going on. It could be hydrogen bonding. It could be a variety of interactions, some kind of van der Waals or London dispersion forces, keeping everything together. But there are interactions of some kind on all sides in the bulk material, or these green spheres here. On the surface, we have unbalanced interactions. Why? Because on most of the sides, there are interactions, again, of some kind. We don't know what. It depends on the surface. But on the surface, we're exposed to air, and there may or may not be any kind of significant interaction going on with the molecules in the air. So there's always room for more interactions, and that's why dirt sticks to us, our skin. That's why hydrogens and alkenes stick to a platinum surface, because the surface is ready to make interactions. It's got unbalanced interactions. It has residual attractive forces, and thus it attracts things. The surface does. So we consider surface interactions in the form of adsorption, because again, the interior of the substance, our interactions are satisfied. Whatever bonding requirements they may be, they're all satisfied, because every little molecule on the bulk material, in kind of bluish green here, it's all satisfied. There's stuff on all sides. But the surface, we can see a yellow-green type of thing here. We're not wholly surrounded by substituent atoms. We've got one part of the atom that is free to bind to other things, and that constitutes a surface. And it will bind to other things. It'll bind to water. It will bind to adsorbed ions, as you can see. We can even make a whole hydration layer of sorts. It all depends on the type of surface and the type of interactions that end up occurring. And we can quantitate adsorption, or the extent of adsorption, by using isotherms. So we can consider adsorption in terms of the theoretical amount of some solute, whether it be gas or a solute in liquid, that gets adsorbed to an adsorbent. So this is either a function of the equilibrium gas pressure, if we're talking about gases, For example, in gas masks, we might consider that. In liquids, if we put an adsorbent in liquids, the function of the concentration of solute comes into play as the theoretical amount of solute that could get adsorbed. And again, isotherms, they tell us how adsorbent and adsorbate interact, not necessarily react, but interact under given conditions. Usually these isotherms are at a constant temperature, but we vary the pressure until we get to maybe a saturation pressure, and we vary the concentration. And that's when we get an isotherm in the form of X over M versus P. P being pressure, X over M. X is mass of gas that gets adsorbed, and M is the mass of adsorbent. The most common of isotherms is the Freundlich isotherm. So gives us the relationship between the quantity of gas adsorbed per mass of adsorbent and the pressure at a given temperature, and it can be expressed using this Freundlich equation, where we have X over M equals K, some constant, multiplied by P, our pressure, to the 1 over N. And again, N is another constant. K and N both depend on the nature of adsorbent, first of all, and the gas or solute at a given temperature. And so we can find those things. But first we can look at what happens with adsorption, Freundlich isotherm style anyway, at given temperatures. So we can have, at constant pressure, we see adsorption will decrease as the temperature goes higher. We start at 195 Kelvin here, we go down to 273, and we can see that the adsorption has decreased quite a bit at any given temperature, pretty much, except for 0. But 10 times 0 is 0. At constant temperature, the saturation is approached. You get to that P saturation, that saturation pressure, and that's high pressure. So in general, we look at the mass per gram of adsorbent, or the mass of adsorbate per gram of adsorbent versus the pressure. But we talk about Freundlich isotherm. It's not valid for every adsorption situation. There are about 5 or 6 different isotherms you could potentially use. We're only going to talk about Freundlich isotherm for now. We could have an entire class on adsorption and surface chemistry. So we can validate the Freundlich isotherm and at the same time get our constants by linearizing the thing. So we take the log of X over M and the log of P, and in this case we consider the log of E, or the natural log here. You could potentially also do this with log 10 as well, but this is the natural log here. So we look at the log of X over M, the log versus the log of P, and we get a straight line. Or if we get a straight line, anyway, the Freundlich isotherm is valid. And then from there, with a slope, we can get 1 over N. So we have our N constant. And at the y-intercept here, we have the log of K, which is our other constant. So we can determine these constants, and then based on the whatever pressure we're at, we can figure out what our X over M is going to be. Now, we're done thinking about Freundlich for right now. There are other things to consider, and I talked about physisorption and chemisorption. They are 2 different things. Physisorption is just a random, non-specific physical interaction. That could be hydrogen bonds, it could be London dispersion forces, hydrophobic interactions, that sort of thing. They are not specific based on, amino acid, one specific amino acid side chain, one specific substrate and binding site. Whereas chemisorption involves some sort of bonding, ionic or covalent. And if it's ionic bonding, we need to consider charge. So pH is going to influence adsorption of charged material onto charged surfaces. And again, this is because of the pKa and the pKb that we talked about earlier in the actual, when I saw you in lecture. So the charge of the proteins is determined by its pKa of all its side chains, and also the terminal amine, the N-terminus, and the terminal carboxylic acid. So we can get a charged protein here at physiological pH. And again, if we have a biomaterial that's present in the body of some kind, it could be an implant of some kind, and we have proteins that are starting to interact with it, if we have charged regions in the material, we could potentially get charged proteins of opposite charge binding to the surface. Chemisorption will occur. So we have electrostatic coupling being the dominant force if we've got charged surfaces and charged adsorbates. And then we can get into, well, what has more affinity to the surface? And, is that going to dominate? And it will eventually because of the Vroman effect. So we have adsorption of proteins on a surface, different charges, and we have a charged surface. So if we have a highly negative surface and a very positively charged protein, like the red protein is going to be more attracted to the surface than, say, the purple protein will. So the higher affinity protein can potentially replace a lower affinity protein. Just because we bind a bunch of purple proteins first does not mean red proteins will come in en masse and start dislodging some of the purple ones, because the red proteins are more attracted. So this will make the surface a dynamic layer that changes over time. So we can consider that if we have, say, a negatively charged surface, the red protein is more positively charged and will have more attraction to the surface, thus can displace lesser positively charged proteins, like the purple one here. And over time, the balance of proteins attached to the surface is going to shift from, say, purple to red. Okay, so we just talked about NMR. In fact, we just had a quiz on it. But here it is again. It bears repeating. And once you get the idea of what's going on, it becomes quite simple. So, if you understand what we're getting at here, the homework probably took you about 10 minutes. So we look at the frequency at which nuclei absorb. And that depends on their local chemical environment. And each chemical environment is different depending on the molecule we're looking at. And you can see that can vary from, say, this alkene here, this dichloroalkene, to this dichloromethane, to kind of a more hydrophilic ring structure, to a more hydrophobic ring structure. The chemical environments are all different, and that puts us at different places when we're putting magnetic fields on these molecules to figure out what's going on. So we can have increased magnetic field with a fixed frequency going from this molecule to the silane molecule, or increasing frequency down this end at a fixed magnetic field. We also consider increased shielding by extranuclear electrons as we go down this way. And you can see how that might be the case here. So we look at, in NMR, we look at two things. We look at relative peak signal height, peak or signal height, same thing, peak signal. And then we look at the multiplicity of the peaks. So we can identify chemically distinct hydrogen atoms in a molecule. So the amount of a signal, or the height of a signal peak, is proportional to the number of identical hydrogens. So in one carbon we have 3 identical hydrogens in this case. This is example A. On this carbon we have 3 identical hydrogens. On this carbon we have 2 identical hydrogens. What makes these identical? Well, this hydrogen is next to another hydrogen, which is next to another hydrogen. This hydrogen next to another hydrogen and next to another hydrogen, if you imagine them in like a tetrahedral type shape. Over here, on the right-hand side, we have a hydrogen that's next to a hydrogen and a fluorine. This hydrogen is also next to a hydrogen and a fluorine. So those hydrogens are chemically distinct, and they're different from these hydrogens. So we have 2 distinct hydrogens, types of hydrogen, in a 1, 2, 3 to 2, 1, 2 ratio. So we would see 2 peaks if we ran NMR on this, one with a height of 3 and one with a height of 2. On this one, we have 2 distinct hydrogens. If we were to imagine the hydrogens being there, we would have a bunch of methyl groups, CH3 here, CH3 here, CH3 here. Those are not chemically distinct from each other, but those are chemically distinct from this central, the hydrogen on this central carbon, which is this one hydrogen. So again, we have 3, 3, 3 hydrogens. We have 9 hydrogens, and we have 1 hydrogen. So we have 2 distinct types of hydrogen, 2 distinct chemical environments present in a 9:1 ratio. So if we ran NMR on this, we have 2 peaks. One is 9 times higher, taller, whatever, than the other one. So the peaks of the methyl groups, the CH3s, are going to be 9 times taller than the peak of this CH here. So your software, your NMR software, will integrate your peaks, and that is what will give you the peak height. Again, the signal strength is proportional to the number of protons with that chemical environment. So we look at this molecule, we have a ratio of 6 to 4. Where does that come from? The 6 is from this chemically distinct environment that has 3 plus 3 is 6. 2 methyl groups with 6 hydrogens total. 4, 1, 2, 3, 4 on the aromatic. And that's another distinct chemical environment. 6 to 4. And then this is H NMR. This is 1H NMR, so this is only looking at the hydrogens. On the second one, again, we have 2 distinct chemical groups. We have the CH2, which is next to a chlorine and a carbon, and 2 methyl groups, which are next to a carbon. This is a 6 to 2 ratio. 3 plus 3 equals 6. And then CH2, 2. Here, again, 2 distinct chemical environments. This methyl group next to this carbonyl carbon, this methyl group next to an oxygen. But there's 3 hydrogens in each, so 3 to 3 or a 1 to 1 ratio here for these different hydrogens in different, all in unique environments, chemical environments. So now we consider spin coupling, NMR spin coupling. So hydrogens attached to adjacent carbons. So you have carbon, carbon, you have hydrogen here, and you have hydrogen here. This hydrogen will affect the possible energy state of this hydrogen. So thus we see, when we run NMR, we see multiple peaks. So, like here, there's only 1 chemical environment, so we get 1 peak. But here we've got 2 distinct chemical environments. We have this hydrogen here, which is next to, the carbon here is next to a CH3. So we have 3 hydrogens, 3 plus 1, it's always an n plus 1. We divide that into 4, we get 4 peaks, and that's what we see. On the other side, we have the methyl hydrogens. We know the peak is going to be taller. We have 3 hydrogens in this chemical environment, but it's next to a carbon with only 1 hydrogen. So we have 1 plus 1 is 2 peaks. And here that is again. The signal from a given hydrogen is split by hydrogens on adjacent carbons. So for n hydrogens on an adjacent carbon, that signal is split into n+1 peaks. So here is this example of fluoroethane again. We have this, which has 3 hydrogens. So the hydrogen signal for this carbon is going to be split. We have 2 hydrogens here. 2 + 1 = 3. So this will be a triplet, this one. This one, on the other hand, is next to a carbon with 3 hydrogens. So these 2 hydrogens will have 3 + 1, 4 peaks. It'll be split into a quartet, or 4 peaks. So here we are measuring this blue hydrogen here. If we have no coupled hydrogen, we only see 1 peak. We have 1 coupled hydrogen. See this, the hydrogen, this red hydrogen here, we have 2 peaks. 2 coupled hydrogens, 3 peaks. 3 coupled hydrogens, 4 peaks. So how do you know your way around the NMR spectrum? If you're just given a spectrum and you have to figure out what the molecule is, what do you need to know? You should probably have some other information first, but you can determine what peaks represent what moieties here. So if I say this NMR spectrum is a representation of chloroethane, how do you know what's what? First we can look at peak height, the number of hydrogens. So this peak is taller than these peaks, taller than these peaks. So this is likely the methyl peak. Whereas the multiplicity, this peak is split into 3. 1, 2, 3 hydrogens plus 1. This neighbors this, so we can assume, because it's split the way it is, and because it's shorter than this peak, we can assume that this is chloroethane. And we'd have to know that there is a chlorine here beforehand, because this NMR is not going to give us that information. Okay, so those are the 2 things that were left over. We will go over whatever you would like if you come to the recitation that we will have on Tuesday. But I'll tell you a little bit about what not to study. We did a lot of inorganic chemistry reactions early on in the semester. There's not going to be any inorganic chemistry really we'll have platinum as catalyst and such, but that'll be in the terms of an organic reaction. So no inorganic chemistry reactions. I already told you will not be calculating the equilibrium constants. Equilibrium constant calculations is something you do using experimental data. We don't have any experimental data, and I wouldn't give you experimental data to process, so we're just not going to do it. Chemical mechanisms. I've told you many times that we're not going to do chemical mechanisms on the exam. We're not going to talk about infrared spectroscopy. We're not going to talk about spectrophotometry, Beer-Lambert law. I just wanted to introduce that to you a few classes ago. But spectrophotometry, Beer-Lambert, that's BNG319. That's coming up. Okay, and finally, as I already told you when we talked about mass spec, we're not going to have any mass spec problems. That is to say, I might say, here are some NMR peaks. The mass spectrometry says that the mass to charge is 80, 86, whatever. So you can assume that the mass of the compound is 86. And then what is it? That you may see. But you won't be asked to do anything with like interpreting mass spec readouts or chromatograms or whatever. You'll only be looking at NMR peaks, not